Okay, college algebra students, believe it or not, we have reached our last chapter. We're going to talk about 12.1, and the idea is what we call systems of equations. So let's go ahead and do some groundwork first, figure out what is a system of equation, the types, what it means to solve them, etc., etc., etc. So let's do some groundwork and some definitions and some lingo. And what I'll do is I'll start this off with an example. Right? So we have a motor oil mix for a chainsaw. Right, is made of a mixture of gas and oil. Right? It took a total of 10 fluid ounces to make the mixture, and the difference between the two substances is 6. How many fluid ounces of each substance should be used? All right, so in this case, what I have are two unknowns. Right? Let's let X be the ounces of gas, and let's let Y be the ounces of oil. All right, and so since we have two unknowns, what I eventually need in order to solve this situation is I actually need two equations. And so the equations in this case are pretty easy, just kind of reinterpret the meaning, right? It took a total of 10 fluid ounces. So much gas, so much oil together, right, created 10 fluid ounces. So that sounds like X plus Y equals 10 to me. All right, so we now, any ordered pair that solves this is a potential situation for what we're talking about. However, we have another equation, right? Because not only is the sum equal to 10, but they tell us that the difference between the two is 6. So that's telling me that X minus Y is 6. And what we have, this is basically a system, right? It's a system of equations because what they're doing, right, these are equations working together, right, to model a situation. So this situation that I have, it's the same situation just said in a couple of different ways. We're talking about the motor oil mix that I'm making for a chainsaw. And one way I can think about it is the sum of the gas and the oil is 10. And another way I can think about it is their difference is 6. And so working together, we should be able to find, right, how much X do I need, how much Y do I need, all right, in order to solve this particular system. So that is what a system of equations is. Very, very famous throughout all mathematics, because when we look at situations, there's, we've been looking a lot with just two unknowns, X's and Y's, but there turns out that there's 3 or there's 4 or there's 5. I can remember, working on some problems where we actually tried to decrease a problem that was a 200 by 200 system, 200 equations with 200 unknowns. So by that time we were definitely using technology, but you're going to get to see a lot of the things here. And so that kind of gets me into the equation types. One way that we recognize an equation is by saying something like a 2 by 2 system, or a 3 by 3 system, or a 4 by 4 system. And heck, you just heard me say that I've worked with systems that are like 200 by 200. What this is basically telling you is the first number is telling you how many unknowns we have, and the second number is telling you how many equations. So this one is a 2 by 2 system because it has two unknowns, X and Y, and it has two equations. This first one and that second one, 2 by 2. We will actually talk about 3 by 3 systems. That's when we have 3 unknowns, an X, a Y, and a Z. And then when we have 3 equations, right, giving a relationship between X, Y, and Z. But there are others that do exist. Just at the time that we have, I'm not going to be that hard on you. Right? And like I said, by the time they start getting to, too big, we're going to eventually start turning to the calculator and doing work there. So, but we're going to look at their kind of under the engine in this section and kind of get an idea, heck, even what the calculator's doing. Another way that we represent systems, not just by their dimensions, if you would, but also their types. Some are called linear, and some are called nonlinear. All right, linear equations are something of the form. Let's kind of go back into our archives. We've seen X plus Y equals C, right? That is a linear equation because if we were to graph it, we would get a line, number one. But number two, so when things become 3 by 3 or 4 by 4, we're looking at a situation where the variable parts, right, are all risen to the first power, and they're not involved in any products or anything crazy like that. So we could have, like, let's consider a 4 by 4 system. Maybe I have something like x plus y plus 2z plus 3w equals 10. Right? This is an example of a linear equation because it looks like this one with just more variables. All the variables are risen to the first power, and I'm not multiplying. I don't have x times y. I don't have x squared. I don't have x divided by y. Right? I don't have wx over z. Right? So those are situations that make us nonlinear. So essentially, when I just have terms being multiplied together. So the variables are all risen to the first power, right? And they're not involved in any products or quotients. That's a dead giveaway that we are talking about a linear system. So if it's a 4 by 4 linear system, that means all my equations kind of look like that, right? If it's a 200 by 200 equation, they look like that, just there's 200 of them in terms of variables and 200 of them in terms of equations. All right, but take your cue from what we learned. I think this was back when 1.1, when we reviewed lines, or 1.2, somewhere back there, right? We reviewed lines, and that's the general form of a line. So a linear system basically has those types of equations. Nonlinear, well, that's basically as the word phrase says there, they're nonlinear. So perhaps I have something like y equals x squared plus 2. And then I have 2x plus 3y equals 7. This is a 2 by 2 system because there's two unknowns and two equations. But see that little x squared right there? That x squared makes me nonlinear. It doesn't fit in that side over there. All right? Or maybe I have x plus y equals 20, but then we are told that x times y equals, let's say, negative negative 20 or something like that. All right, and so now again, this is a 2 by 2 system, but because I have a product of variables, it's no longer linear. All right, so there's two ways that we can categorize a system: by its dimensions, how many unknowns and how many equations, and whether it's linear or nonlinear. In 12.1, and for most of our work, we're going to be working with linear systems because they're the easier ones to work with. Nonlinear situations we'll look at later, all right, when we get there. But there at least is what we have. Okay. Another terminology is, what does it mean to solve a system, right? What does it mean to be a solution to a system of equations? Well, remember what it meant to be a solution is I have to find a value. In this case, I have to find values, right? Because there's more than one variable. I plug them in, and what I get are true statements, but not just one true statement. I'm trying to find an ordered pair, x, y, that makes that situation true and makes that situation true. So if I find an ordered pair that when I plug it in makes everybody true, then I have a solution. All right. So if I have an ordered pair that makes one guy true and the other one, I don't. So let me change pens here, right? Let's just let me give you a data point, right? Let's try 5, 5, right? So 5, 5, right? When I plug it in here, 5 plus 5 is equal to 10, but down here, 5 minus 5 is equal to 0. So that is not a solution to that system, because it only makes one true. To be a solution, I have to make both situations true. All right? And this one's easy enough. Well, I'll show you some techniques, but does anybody see the solution there? What it might be? Right? Yeah, let's try 8, 2. Right? 8 plus 2 is 10. Check. And then 8 minus 2 is 6. Check. So there's our solution to this system. It's the ordered pair. It's the x and the y value, right? I found them for you, that when I plug them into both equations, they make them both true. It's a solution. So that's what it means to be a solution to a system. I've got to basically solve all the equations. Some other lingo that comes with this topic is what we call consistent or inconsistent. I will talk more about these as we move along, but right now, layman's term, consistent means that a solution exists. Okay, it might be one solution, it might be two, it might be three, it might be infinite, but a consistent equation, right, or a consistent system has a solution. Some solution, some ordered pair exists. Inconsistent means that there is no solution. No matter how hard we try, no matter what we do, right, mathematically I can never find a value that when I plug them in makes everybody true. Right? We call those types of systems inconsistent. And as we do work, you'll actually see that, and I'll use the lingo as we go along. Right? So there you have it. Most of these situations, I kind of made just a nice, simple canned application. But as you guys move through your math careers, many, many word problems turn into systems of equations because there's more than one unknown. And if I have more than one unknown, I need to build at least as many unknowns that I have. So we start building 2 by 2, 3 by 3, 4 by 4, 5 by 5, 200 by 200 systems of equations. There's two types, linear and nonlinear, solutions, ordered pairs or triplets that work, and then consistent systems have solutions, inconsistent systems have no solution. So there's some of your terminology with regard to systems. Right now, let's go ahead and put this terminology to work and get to business. See you guys soon in some videos.